The sister teams 11419 and 19897, Jasper rolls blue and white from Plano, Texas. We'll be talking about the basics of robot design and their process for robot design. Jasper rolls blue and Jasper rolls white are two veteran teams from Jasper High School, and having competed for 5 seasons, they have earned numerous awards in design and outreach. Jasper rolls blue claimed the Texas UIL State Championship in the Center State season and served as finalist alliance captain in the Sapphire Division of last year's North Texas Regional Championship. Please welcome sister teams Jasper rolls blue and white.
Hey, Jasper. Hello, everyone. Firstly, I'd like to thank Technic Buds for allowing us to present at this very prestigious event. So thank you for that. I'd like to introduce us as a team. I'm going to take Patel from Jasper Wolves Blue, and today we'll be presenting the design process and how we implement it. My name is Alma, and I think we can skip these next 2 slides.
We're talking about the design process and so we'll be talking about this. What is the design process and why is it crucial for FTC teams? Design process is really useful for the FTC team because it organizes and is used for time management and it helps create an effective and reliable solution for robotics. So generally in the design process we have 6 steps. We start off with defining the problem. Now the case is going to be the competition. I'm taking the last season's example of PCB. In the competition, we're given simple tasks like hanging the specimen onto the lines, collecting the samples from the submersible, and storing them in the basket. Now, after we define the problem, we're going to go into generating the concepts, basically taking different ideas and combining them to create a solution. After the second step, we're going to go into designing the solution. We use a 3D software called Onshape or Vision 360, which my friend Clark is here, we're going to later on. And that's where we basically create a solution online. After creating a solution online, we're going to go to the next part, which is building and testing. This is where builders and coders collaborate together to create a physical prototype of a robot. After building and testing, we evaluate the solutions. We make sure that the robot is up to task, is able to finish all the requirements before the competition. If it's able to do that, then we're good to go to the competition. If not, we go back and see working, where is it lacking, and all of that. It's an iterative process. And at the end, the 6th step is presenting the solution. This is basically the competition. We go and see if it's working or not.
Okay, now let's talk about the engineering basics. So, you might be thinking, what is CAD? CAD is computer-aided design, and it allows designers to visualize what they're going to build before they actually do it. This not only enables designers to know the full range of motion and robot functions, it also allows it to speed up the R&D process because now the devs know what exactly to code and what robot functions to develop. Now, we can CAD complex things, but fabrication is just as important. And there are 2 ways that you will manufacture things to get a part. First is additive manufacturing. This is using a raw material like plastic filaments to make a complex and intricate product, like a clock. And another thing that you'll use is subtractive manufacturing, where you'll take a body and remove material from it. And that is something like the CNC milling or laser cutting. Now, let's talk about basic hardware that you need once you've got your chassis fitted. So first, you will use some motors and sensors, and this helps with obviously the mobility of the robot. And the thing is, servos are much better for certain uses, such as arms, and certain movement claws, because it's precise and it has and it's used and it has and it's good for lightweight pieces. And motors are used for chassis and slides, which make it much better for heavyweight and far more efficient. Now there are sensors, and these help with spatial awareness and object detection. We can use cameras, sensors, and color sensors, and odometry pods, which help the robot do this.
Skip that slide.
Okay.
Now, we talk about where new FPC should start before building and designing their robot. Before designing or building a robot, you should probably look into social media platforms like YouTube, Discord, or other platforms to see how different robots are performing. Looking from simple to complex mechanisms and see what's right for your robot. Now, these simple and complex mechanisms could be claws, arms, like Haji and Aditya were talking about, and then you can incorporate these in your robot so that you can successfully compete in the competition. And we're going to talk about our design journey as a team. So where did we start? We started off as looking at observing different robots at different competitions and then see where they're performing best. Because we can always improve on them by looking at others, right? So we have different general trends on the different competitions, lots of claw, intake claw, and single claw. And we because that.
Okay, somebody else hold the thing for. No, the other end. It's the other side. It's way there.
Otherwise, something else.
And the thing in his hand that it weighs. Just hand him that. There.
Alright, so what I'm saying is, during these competitions, we find the general trend as to be claw to claw, intake to claw, and single claw mechanisms. And our software team focused on single claw mechanisms, while we focus on all three of them. And claw to claw mechanism is basically using two claws to pick up the specimen and then hang them. And then the other one is single claw mechanism, which is basically using one claw to do both sides. So on the Jasper robotics white side, we had 4 different versions of a robot. The first 2 had separate intake and outtake claw, which is very not efficient compared to the third and fourth version, where they are in the same they had more interactions with each other, which allowed us to gain more points and scoring for specimen or putting the capsules to baskets. And one thing we can definitely improve on is focusing on one thing rather than focusing on 3 different things, because it's very complex and it's very frustrating because you focus on one thing, finish that first.
This way. Yeah.
So, this is our sophomore journey through last season, and they focus on one thing, like we said, and because of that, they had a solid platform, and you can see that in D1, which is at the top. And then they moved on to B2, where they could add more stuff because they already perfected one task. That is a very important lesson for those rookie teams out there. And then in the third one, they fixed their second one's problems and even added new materials like carbon fiber, which helps it operate much better and efficiently while also improving speed.
Alright, so now we're talking about what we also did during off season. So during the off season, as you can see to the right of part of it, we have this one robot that we decided to make an improvement from the sophomore's robot that we had, right? One of the issues with the sophomore's robot was that they didn't focus that much on wiring, right? So they used a coiled wire, however, it was from a USB charger, which only tolerates 5 amps, whereas the amount of power the control pump sends to the servos is like, and motors is approximately 30 amps, right? And so they tried a couple of fuses during competition, and they realized later on in the competition that this was an issue. So we tackled this wire management issue by using different drag chain basically. This drag chain allows us to compact all the wires, and slides extend, then the wires also extend and retract with the slides. And then we also competed in a CAD competition where we used a similar mechanism, the pivoting slide mechanism that sophomores had and that we use. And so this is really good, this pivoting slide mechanism, in that it's one mechanism that you can use to focus on multiple tasks at once. Like, for example, if the slides come down, then they can grab from the submersible, put in the back basket, or they can grab specimens and hang it onto the high chamber or chamber. And then this is just our freshman team squad journey that we had. You can see how raw and unrefined first claw, and as we progressed, we learned from our mistakes that the first claw wasn't too stable and it kept coming apart during competition. And as you can see, it improved over time as we learned from our mistakes and looked to our mentors for suggestions about our claw and robot design as a whole. And I don't think this was the updated slideshow, so I will just add one of the things that we have on that, right? So in the past seasons, very recently, there's been many teams who use custom chassis. And so one very common version of the custom chassis is a parallel drivetrain, right? Now, why should I do a custom chassis when we can buy parts from GoBuilder and just put those together? Well, you should do a custom chassis because you can customize how far each of the holes and each of the motor placements are, right? Where you have the GoBuilder U channel, for example, like this, right? There's pre-positioned holes on the U channels which don't allow you to have as much customizability as if you just CAD the parts yourself, right? And there are many, and like Karthik mentioned earlier, right? We use the subtractive method with laser cutting to make all these shapes from a sheet of metal, right? And also when you're doing custom chassis, it's very important to pocket, right? Especially when it's metal, because if you don't do pocketing, then your robot will be extremely heavy. So we'll just go over some do's and don'ts, really quickly, some of our mistakes that we made. And so some things you should really do is choose one task at the beginning and perfect that, especially the one that gains the most points, like hanging specimens, right? And then make sure that you can robot so that you can visualize how your robot is going to function digitally. Make the design as simple as possible, right? The sophomore's robot, the slides were able to come down and extend. It only had one mechanism that could do all the tasks, right? It was simple and it was efficient. And then learn from your previous design mistakes, right? Because it's an iterative process, like I've said, right? You make one mistake, it's fine, just improve upon the next one. And then some things you definitely should not do. Don't try to accomplish all the tasks right off the bat. This is a very big mistake. Try to attempt that, then you will run into a lot of mechanical errors. Don't skip the CADing process. It's very crucial. The freshman team did that a little bit, and we ran into a bunch of mechanical errors. And make sure to don't change your design when it has yielded you a lot of points, right? One of the mistakes the sophomores made was they changed the design for UIL State Championship, but unfortunately it had a slight flaw, like a fuse volume, and so it wasn't able to perform as well as they did on the test match, on the practice field at school. And then don't change your design at the last second. If you do so, then there's going to be unforeseen errors that you won't be able to fix at the match. And then there's a very good engineering principle that many engineers use in their professions called KISS. I know it's not that kind of KISS, Keep it simple, stupid. Basically, the more simpler your design is, the more efficient your robot or machine will be able to operate, right? The stupid part is just a reminder that things can go wrong, especially when you complicate the robot. And doing this will allow you to reduce costs drastically. And I'd like to conclude with a quote that our coach, Mr. Woods, loves to say all the time: under promise and overachieve. Thank you.